Physics 2425 is a calculus-based physics course, and so the expectation is that you've already completed calculus. I know sometimes with students at Angelina College, you may just be taking calculus concurrently. So I want to go over just basic derivatives of polynomials today. So this early in the semester, that's probably all we'll need. Later in the year, we might want to be able to take derivatives of sine and cosine, but that's probably not until we get to waves. So first thing we want to understand is the derivative can be written in a couple of different ways. I'll look at both of those. And so let's just start with a simple function. Suppose we have the function y equals x to the 7th. The rule says that the derivative, which can be written like this, for any polynomial, let's go more basic, y equals x to the nth, we can write that as dy dx. That means the derivative of y with respect to x, it will equal n times x to the n minus 1, or that can be written as y prime. So in our example here, if y is equal to x to the 7th, then the derivative will be 7 times x to the n minus 1, to the 6th power. If we put a constant out in front, suppose I have y equals 3 t to the 5th, the constant just multiplies. The derivative y prime would be 3 times, and then the derivative of t to the 5th is 5t to the 4th power. So I end up getting that the derivative is 15t to the 4th. One answer, there's the other answer. Whoops. Okay. Now, those were both monomials. A polynomial is just a string of monomials. So we may have a function like x of t equals 8 to the 4th minus 3t squared plus t minus 6. So now instead of one monomial, we have 4 monomials. The derivative, written x prime of t, would be 8 times, the derivative of t to the 4th is 4t cubed, minus 3 times, the derivative of t to the 2nd is 2t to the 1st power, just 2t. The derivative of a constant like this, t, is just 1. And the derivative of negative 6, or any constant number, is 0. So our derivative is 32t cubed minus 6t plus 1. Now, one of our big applications of derivatives early is the relationship between position, velocity, acceleration, and how those functions, they're all functions normally of time. So position is typically going to be represented as either a function of x or y, depending on whether we're doing a problem that's horizontal, which is probably most of the time, or vertical. So we would let that generally be x is t. That says the position is a function of time. That implies that the position may be changing. The velocity would be v of t, but that's equal to the derivative of the position. In other words, x prime of t tells us how the position is changing with respect to time. A change in position means you have velocity. Acceleration can be written as a function of time a of t. Acceleration tells you how the velocity is changing with respect to time. Acceleration is v prime of t, or we can think of that as being the second derivative of the position. The second derivative is when you take a derivative of a derivative. So that's the relationship between position, velocity, and acceleration. Suppose I tell you that I have a position vector, a position function that's represented by 4.9 t squared plus 3t minus 18. If somebody wanted to know a function for that velocity, well, first of all, what if they wanted to know the position? If I want to know the position at a particular time, let's say I want to know it at 4 seconds, I want to know the position at 4. I would put 4.9, 4 squared, 3 times 4, minus 18. Now I'd get out a calculator because I'm like everybody else. Let's do it the easy way. 4.9 times 4 squared plus 3 times 4 minus 18 comes out to be 72.4 meters. I'm not going to worry about significant digits in this function right now, but just plugging in 4, that's what I found out. Now, if I want a velocity function, I take the derivative. The derivative of 4.9 t squared is going to be 2 times 4. Will be 4.9 times 2t plus 3. So the velocity at 4 is 9.8 t plus 3. I'm sorry. My phone's ringing, but I'm ignoring it. So the velocity function is 9.8 t plus 3. If I want to find the velocity of 4, I would plug that in. Again, I can get out a calculator to help me figure out quickly what is 9.8 times 4 plus 3, and I get 42.2. That's going to be in meters per second. If I want to get the acceleration that's related to this, I know that the acceleration function is the derivative of the velocity function. My velocity function is 9.8t plus 3. Well, the derivative of 9.8t plus 3 is just 9.8 meters per second squared. Notice in this case, the acceleration is a constant. It didn't actually depend on time. So the acceleration at 4 seconds would be 9.8 meters per second squared. Okay, I hope that kind of serves as a refresher on how to take a derivative of a polynomial, as well as an introduction to this idea that position, velocity, and acceleration are related by derivatives. A derivative tells you the rate of change. So the rate of change of position, that would be x prime, is velocity. The rate of change of velocity, v prime, is acceleration.